In complying with the landing requirements, JAR Ops 1 states that the operator must take account of the altitude at the aerodrome, not more than 50% of the headwind component or not less than 150% of the tailwind component, and the operator must account for the runway slope in the direction of landing if greater than plus or minus 2%. An important landing requirement is the one that addresses landing on wet or contaminated runways. JAR Ops 1 states that if weather reports or forecasts indicate that the runway at the estimated time of arrival will be wet or contaminated, the landing distance must be at least 115% of the dry landing distance. In other words, on wet or contaminated runways, the landing distance must be increased by 15% or by a factor of 1.15. However, JAR Ops 1 also states that a value of less than 115% may be used if the aeroplane flight manual includes specific information about wet or contaminated runways. Even though the landing distance increases on wet or contaminated runways, the aeroplane must still be able to demonstrate it can stop within 70% of the runway for turboprops and 60% of the runway for turbojets. Therefore, just be sure you understand the implications of this. Now let's work through an example. If dry landing distance of a turbojet aeroplane is 920 meters, what would the minimum landing distance available have to be if the runway was wet? Since the runway is wet, we have to increase the landing distance by 15%. We do this by multiplying 920 meters by a factor of 1.15. Therefore, the wet landing distance is 1058 meters. JAR Ops stated that the landing distance must be within 60% of the landing distance available. Therefore, to find what minimum length of runway is needed, multiply 1058 by the factor 1.67. This gives an answer of 1767 meters. Therefore, if the runway is wet and the dry landing distance is 920 meters, then the minimum length of landing distance available at the airfield must be 1767 meters. In fact, we can simply summarize to say that for jet aeroplanes, the combined wet factor and regulation factor is 1.92, and for the turboprop, this factor is 1.64. One of the last landing requirements is about the dispatch mass, which we have already looked at in previous lessons. The dispatch rules for Class A aeroplanes are found in JAR Ops 1.515 paragraph C, and state that for dispatching an aeroplane, it must be assumed that, firstly, the aeroplane will land on the most favorable runway at the destination airfield in still air, and secondly, that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction. If the still air requirement cannot be met, the aeroplane may be dispatched only if there are two alternate aerodromes at which full compliance of the regulatory dispatch requirements can be met. These dispatch regulations may sound a little complicated, so let's examine them further. The first assumption is that the aeroplane will land on the most favorable runway in still air or zero wind. This means that, assuming zero wind at the destination airfield, the runway which would accommodate the largest possible landing mass would be selected, since that is the most favorable runway. In our example on screen, assuming zero wind, runway 04 and runway 22 both allow a maximum landing mass of 51,000 kilograms, but runway 31 and runway 13, being much shorter runways, allow a maximum landing mass of only 43,000 kilograms. Therefore, the most favorable runway in still air is either runway 04 or 22, which both allow a maximum landing mass of 51,000 kilograms. The second dispatch assumption is that the aeroplane will actually land on the most likely runway to be assigned considering the probable wind speed and direction. In this case, runway 04 has a strong headwind for the landing, which will allow the aeroplane to land at a much greater mass than if there were no wind. In our example, the headwind has increased the maximum landing mass to 52,500 kilograms. However, runway 22 has a tailwind, which will decrease the maximum landing mass to 47,800 kilograms. Runway 31 and runway 13 both have a full crosswind. Therefore, the maximum landing mass for these two runways will be the same as for still air. If the second dispatch assumption is that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction, then it would have to be runway 04 with a maximum landing mass of 52,500 kilograms. In summary then, the first assumption requires that the pilot select runway 04 or 22 for a maximum still air landing mass of 51,000 kilograms, and the second assumption will require the pilot to select runway 04 for a maximum landing mass of 52,500 kilograms. Now, we need to consider what to use as the dispatch mass of the aeroplane. If the aeroplane was dispatched at 52,500 kilograms mass, and then on arrival at the airfield, the forecast wind was not experienced and was less than 15 knots, the aeroplane would not be able to land. Therefore, the aeroplane must be dispatched with a mass of 51,000 kilograms. Dispatching the aeroplane with this mass would mean that, no matter what wind conditions prevail at the destination airfield, the aeroplane will have a mass which will allow it to land. The way to simplify the dispatch rule is always consider the greatest mass in still air and the greatest mass in the forecast wind conditions, and, of the two, take the lesser mass as the dispatch mass. Of the two, it is the still air mass that is usually the lesser mass, as shown in our example. The exception is when there is a tailwind on a unidirectional runway. A unidirectional runway is a runway whose direction for takeoff and landing is fixed in one direction, and in this case, the maximum landing mass in the tailwind will be less than the maximum landing mass in still air. Before we finish this lesson, let us work through the landing graph in CAP 698, which is on page 46 of section 4. As with all graphs, before you use them, look around the graph for any associated conditions or assumptions and identify any correction information. In this case, there is a correction for manual spoilers since the graph assumes auto spoiler deployment. To start our example, let us assume the landing distance available of 2,400 meters. Therefore, move upwards from 2,400 meters until the reference line for wind. For tailwinds, move down and left along the sloping guidelines, and for headwinds, move up and right. We'll assume a headwind of 20 knots, so move up and right along the sloping guideline until you reach 20 knots headwind. Then move straight up to the next reference line, which is for the runway condition. If the runway is dry, simply travel vertically upwards. However, if the runway is wet, which is what we will assume, travel up and left to this point. Then move up vertically to the next reference line, which is for the flap position. For flap settings of either 30 degrees or 15 degrees, move up and left along the guideline, but for 40 degrees flap, which is what we will assume, move straight up through the flap section until you reach the pressure altitude of the airfield, which in our example is 2,000 feet. From this point, move horizontally to the right and read off the field length limit landing mass. In our example, the field limit landing mass is 46,800 kilograms. Most Class A performance graphs, such as this one, already have all the necessary regulation and wet factors already applied. Therefore, in this case, since it is an example graph for a Boeing 737, the landing mass of 46,800 kilograms ensures that the aeroplane will be able to achieve a full stop landing within 60% of the landing distance available. Exceeding this mass will mean that the aeroplane cannot meet the landing distance requirements. However, there were other requirements that the aeroplane had to meet. Remember that the aeroplane must also ensure it can meet the landing climb requirements. From an example we went through earlier, Let's assume the landing climb limit mass is 61,800 kilograms. There is one more mass to consider. The structural limit landing mass of the 737-400 series is 54,900 kilograms. Exceeding this mass may structurally damage the aeroplane during the landing procedure. Therefore, the maximum landing mass for our example must be the lowest of the listed masses, and in this case, it is 46,800 kilograms. This completes the lesson on the Class A performance requirements for the landing phase of flight. Make sure you are able to work out the aeroplane's landing distance and landing distance available using the factors we mentioned. These form a significant part of the exam. Also, ensure you are very familiar with the landing graphs, and again, expect questions to test you on the use of these graphs. Make sure you dedicate a significant part of your time carefully going through questions in the period leading up to the exam.